Think about the last time you bought a bag of salad greens or a clamshell of cherry tomatoes at the grocery store. You probably glanced at the label, saw something like "Grown in the USA" or "Locally grown," and dropped it in your cart without another thought. But here's what that label is not telling you. A growing percentage of the vegetables you buy at modern grocery stores, the lettuce, the spinach, the tomatoes, the cucumbers, the herbs, were never grown in soil at all. They were grown in water, in a climate-controlled building with no sunlight, no rain, no seasons, and no dirt. In a system so precise, so data-driven, and so unlike anything traditional agriculture has ever attempted that it genuinely feels more like a laboratory than a farm. And the companies building these systems are spending 10, 20, even $50 million on a single facility because they believe, and the science increasingly agrees, that this is what the future of food production looks like. Today, we are going inside that world, the technology, the science, the extraordinary economics, and the real human story behind the hydroponic greenhouse revolution that is quietly changing what ends up on your plate. Let's go. Hydroponic farming, the practice of growing plants in nutrient-rich water solutions without soil, is not a new idea. Its theoretical foundations stretch back to experiments conducted in the 17th century, and commercial hydroponic production has existed in various forms since the mid-20th century. But what is happening right now in the controlled environment agriculture industry represents something genuinely new, a convergence of sensor technology, artificial intelligence, LED lighting innovation, and large-scale private investment that is producing facilities of a scale, efficiency, and output quality that simply did not exist 10 years ago. The global indoor farming market was valued at over $40 billion in recent years and is projected to grow dramatically as climate uncertainty, water scarcity, and the global demand for year-round fresh produce drive investment into systems that can grow food independent of weather, season, and geography. The largest hydroponic greenhouse operations in the world today cover multiple acres under a single roof, produce millions of pounds of vegetables per year, and operate with a level of environmental control that makes traditional outdoor farming look almost primitive by comparison. Before we get into how a large-scale hydroponic greenhouse actually works, you need to understand something about why this technology is being taken so seriously by investors, food companies, and governments around the world. And it comes down to three converging pressures that traditional agriculture is genuinely struggling to solve. The first is water. Conventional field agriculture uses an enormous amount of water, most of which is lost to evaporation and runoff. A well-designed hydroponic system uses up to 90% less water than field production of the same crop because the water is recirculated in a closed loop. The plant takes what it needs, and the rest goes back into the system. In a world where freshwater scarcity is becoming one of the defining agricultural challenges of the 21st century, that number is not a marginal improvement, it is a transformation. The second pressure is land. Vertical hydroponic systems can grow crops in stacked layers, effectively multiplying the productive area of a single footprint by 10, 20, or even 30 times compared to a field. In densely populated regions near major cities where land is expensive and limited, this density advantage changes the economic calculation of local food production entirely. The third pressure is consistency. A hydroponic greenhouse in Minnesota can produce the same quality of basil in January that a farm in California produces in July, because the growing environment inside the greenhouse is the same regardless of what is happening outside. For food manufacturers and retailers who need consistent supply, consistent quality, and consistent size and appearance year-round, this reliability is genuinely transformative. A large-scale hydroponic greenhouse begins with the building itself, and modern controlled environment agriculture facilities are engineering achievements in their own right. The structure is designed to maximize light transmission while minimizing heat gain in summer and heat loss in winter, using specialized glass or polycarbonate panels, thermal screens that deploy automatically, and in many facilities, a complete shift to LED artificial lighting that replaces or supplements natural daylight entirely. The environmental control systems, heating, ventilation, air conditioning, carbon dioxide enrichment, and humidity management run continuously and are managed by computer systems that monitor hundreds of sensor data points across the facility in real time. Carbon dioxide levels are elevated above atmospheric concentrations to accelerate plant growth, a process called CO2 enrichment that can increase yields by 20 to 30%. Temperature, humidity, and light intensity are dialed to the precise optimal conditions for whatever crop is being grown, and those conditions can be changed remotely by a farm manager looking at a dashboard on a smartphone. The nutrient delivery system is the heart of the hydroponic operation, and this is where the science becomes most visible and most impressive. Instead of drawing nutrients from soil, hydroponic plants receive a precisely formulated liquid nutrient solution delivered directly to their roots. The composition of this solution, the exact ratios of nitrogen, phosphorus, potassium, calcium, magnesium, iron, and dozens of micronutrients, is calculated by agricultural scientists based on the specific crop variety, its growth stage, and the production targets of the operation. The solution is mixed in large tanks, monitored continuously for pH and electrical conductivity, adjusted automatically when sensors detect deviation from target parameters, and delivered to plants through one of several hydroponic methods: deep water culture, where roots hang directly in aerated nutrient solution; nutrient film technique, where a thin stream of solution flows continuously past the roots; or substrate systems like rock wool or coco coir, where roots grow in an inert medium fed by drip irrigation. On a large commercial operation, the nutrient management system is a continuous automated operation that makes thousands of micro adjustments per day that no human team could replicate manually. In vertical farming operations, the most capital-intensive expression of hydroponic growing, the crops are grown in stacked horizontal layers inside a fully enclosed building with no natural light at all. LED lighting panels above each growing layer provide the precise spectrum and intensity of light that the plants need at each stage of growth. And the light recipe, the specific combination of red, blue, and white wavelengths delivered at specific intensities for specific durations, is programmed for each crop variety based on extensive research into how plants respond to different light conditions. A head of lettuce in a vertical farm might receive a precisely calibrated 12 to 16 hours of optimized LED light per day and be ready for harvest in as little as 21 days from seeding, roughly half the time it would take in a field. That speed, multiplied across millions of plants growing simultaneously in stacked layers, is what makes the economics of vertical farming even theoretically viable despite the enormous energy cost of the lighting systems. Harvest in a large hydroponic greenhouse is a combination of automated systems and skilled human workers that looks genuinely unlike any other agricultural operation. In lettuce and leafy green production, automated harvest conveyors carry growing trays from their positions in the growing area to a central harvest station, where workers cut the mature plants with precise, efficient movements, place them directly into packaging, and the sealed packages move immediately into refrigerated storage. The entire process from cut plant to sealed refrigerated package can happen in under 2 minutes. In tomato and cucumber production, harvest is done entirely by hand by trained workers who move through the crop rows on elevated platforms or automated transport systems, picking fruits at precise stages of ripeness using color, firmness, and size as guides. The skill of the harvest worker in a hydroponic greenhouse is different from a field harvest worker, but no less real. Reading crop ripeness, maintaining harvest quality standards, and operating within an environment where every surface is clean, every process is documented, and food safety compliance is measured in real time. The economics of large-scale hydroponic greenhouse production are genuinely complex and remain one of the most intensely debated topics in modern agriculture. A $10 million greenhouse facility can produce remarkable quantities of high-quality fresh vegetables year-round, but the capital cost, the energy cost of lighting and climate control, and the skilled labor cost of managing a sophisticated, technology-driven production system all add up to a cost structure that is significantly higher than conventional outdoor production. This is why hydroponic produce typically sells at a premium and why the business model depends on capturing that premium consistently through product quality, local sourcing appeal, food safety certification, and brand positioning. Many early large-scale vertical farming companies have struggled financially, despite their technological sophistication, because the gap between production cost and viable retail price has been harder to close than initial projections suggested. The companies succeeding in this space today are those that have found the right crop mix, the right market positioning, and the operational efficiency to make the economics work without compromising the quality that justifies their premium pricing. The people who work in large hydroponic greenhouse facilities are a genuinely new category of agricultural worker, part farmer, part laboratory technician, part manufacturing floor operator. The crop production team monitors plant health through daily scouting using integrated pest management techniques adapted for indoor growing environments where chemical pesticide use is tightly restricted, and biological controls, beneficial insects released into the growing environment to control pests naturally, play a critical role. The data science and systems engineering teams manage the facility's environmental control and nutrient delivery systems, analyzing sensor data streams to optimize growing conditions continuously. And the harvest and packing teams operate in an environment that looks more like a food manufacturing facility than a traditional farm. Hairnets, gloves, temperature monitoring, and documented food safety protocols governing every step. This workforce is diverse, often multilingual, and concentrated near the urban centers that hydroponic facilities deliberately locate themselves close to in order to minimize transport time and maximize freshness claims. The communities around large hydroponic facilities have found stable year-round employment opportunities that seasonal outdoor agriculture cannot offer, and that stability is one of the most underappreciated social benefits of the controlled environment agriculture model. The challenges facing the hydroponic greenhouse industry are real and significant. Energy consumption is the most fundamental. LED lighting, climate control, and pumping systems make large hydroponic operations significant electricity consumers, and in regions where the grid still runs on fossil fuels, the carbon footprint of hydroponic production can exceed that of conventional field farming despite the water and land advantages. The capital cost of building and equipping a sophisticated greenhouse facility remains a barrier to entry for smaller operators and has led to a concentration of investment in large venture-backed companies whose financial stability has sometimes proved fragile. And the range of crops that hydroponic systems can produce economically remains limited. Leafy greens, herbs, tomatoes, cucumbers, and strawberries are the commercial mainstays, but staple crops like grains, legumes, and root vegetables remain economically impractical in hydroponic systems at any meaningful scale. The future of this industry almost certainly lies in improving energy efficiency through better LED technology and renewable energy integration, reducing capital costs through improved facility design, and expanding the range of economically viable crops through continued research into growing system optimization. The next time you pick up a clamshell of leafy greens at a grocery store and see the words "grown locally" or "grown without pesticides" on the label, think about what is actually behind it. A building full of sensors and LED lights and recirculating nutrient solution and stacked growing layers where the weather is whatever the computer says it should be. A team of scientists who spent months dialing in the exact light recipe and nutrient formula that makes that specific variety of lettuce grow faster and taste better than it would in any field. A harvest worker in a hairnet who cut that plant and sealed that package in under 2 minutes, and an investment of millions of dollars placed on the bet that this, not a field, not a season, not the rain, is where the future of fresh food is going. That bet is not certain, but it is not crazy either, and understanding it changes the way you think about every vegetable you have ever bought. That is not just a bag of salad, that is the future of farming, tested in real time at massive scale right now.